Good morning, one and all. My name is Dr. Devi Manjunatha. I am working as a senior professor in the Department of Electronics and Communication Engineering, Alvas Institute of Engineering and Technology, Moodbidri, Bangalore. Let us discuss the previous session, what we discussed. In the last session, we studied the following: the maximum ratings of operational amplifier, which we discussed as it operates on plus or minus 4.5 volts to plus or minus 18 volts. We discussed that, power ratings and all we discussed. And we discussed also the characteristics of ideal operational amplifier, which is very important for a operational amplifier. Then block diagram of operational amplifier we discussed, and the concept of virtual ground. So, the concept of virtual ground exists only for ideal operational amplifier, and with the concept of virtual ground we also discussed inverting op amp or inverting amplifier using operational amplifier. What are the learning outcomes of this session? Today we are going to discuss on non-inverting op amp or the inverting amplifier, the operational amplifier applications, and also we discuss operational amplifier voltage follower and op amp adder circuit. So, these are the outcomes of this session. Next, let us discuss on non-inverting op amp or non-inverting amplifier. We already discussed on inverting amplifier or inverting op amp. What is inverting amplifier? It is an amplifier, it is an operational amplifier circuit whose output is proportional to inverted version of the input. So, that is inverting amplifier. Now, what is non-inverting amplifier? The non-inverting amplifier is an amplifier circuit whose output is proportional to the non-inverted version of the output. That means, we will get the amplified version, but not inverted version of input at the output of the non-inverting amplifier. Let us see the circuit diagram of non-inverting amplifier. So, this is the circuit diagram. Let us use the board and explain what is non-inverting amplifier circuit, all those things. So, this is the operational amplifier. Positive, negative. Okay, let us write negative here, positive here. We will apply the signal here. We can call it as Vi as the input, and there is a negative feedback as seen in the negative inverting amplifier. This is V0 and this is grounded. Let us call this as R1, let us call this as RF. As we have discussed, let us call this point as G, node G, and here the current flowing is I1, here the current flowing is I1. The current flowing into the operational amplifier we call it as II, and the current flowing through RF let us call it as IF. Now, the moment we write input like this means it is like this. So, this is a sinusoidal input, we will apply positive is here, negative is here. That means, what will be the input? Some unamplified input signal, weak signal, which we will going to apply here. This is T and this is Vi, let us call. At the output we must get amplified and non-inverted version we should get, then only we call this circuit as non-inverting amplifier. So, we have seen here I1 is the current through R1, IA is the current into the operational amplifier, IF is the current flowing through the RF, and Vi we will apply some weak sinusoidal signal at the input point, positive terminal, and V0 is the output which we will get at pin number 6 of operational amplifier. This is op amp. So, Here the circuit details we have to write. First we have to give the definition. Let us all follow this flow. First we will give the definition. What is the definition of non-inverting amplifier? Non-inverting amplifier is an amplifier whose output is proportional to the non-inverting version of the input. That means we need to prove that V0 is proportional to Vi. So this is what is the non-inverting amplifier. Second one, circuit diagram. We have to write the circuit diagram. Then we have written the circuit diagram. This is the circuit diagram. Third one, we need to discuss the circuit details. Circuit details. Whatever you see on the circuit diagram, you can just explain in 2 lines. So the circuit diagram of operational amplifier is as shown. Here the resistors R1 and RF are 2 external resistors. R1 is connected to inverting input terminal. RF is connected in the feedback path, which is a feedback resistor. The input is given to positive terminal of the amplifier, operational amplifier. Therefore, it is called as non-inverting amplifier. And V0 we take at the output point. Here the current I1 is the current flowing through R1. II is the current which is flowing into the operational amplifier. IF is the current flowing through the RF feedback resistor. So this is what is the circuit details. And also here the op amp works in non-inverting mode of operation. The op amp works in non-inverting mode of operation. What is this non-inverting mode of operation? In non-inverting mode of operation, we give the input signal at the positive terminal of the operational amplifier. Whatever we apply the input at positive terminal of the amplifier, operational amplifier, it gets amplified at the output but not inverted. Then we say that operational amplifier is working in non-inverting mode of operation. So that is the circuit details which we have discussed. Now, next fourth terminology here is circuit analysis. Circuit analysis. So here circuit analysis means we must prove that this circuit works as non-inverting amplifier. That means we need to show that V0 is proportional to Vi. So that's what is our aim in the circuit analysis. Then finally we will conclude that the above circuit works as non-inverting amplifier or the non-inverting op amp. So let us now move on to circuit analysis. So in the circuit analysis, as I told you, we must prove that this above circuit should work as non-inverting amplifier. So as we moved in inverting amplifier, in the same manner, let us just do the analysis here. At node G, I will apply Kirchhoff's current law. So let us apply Kirchhoff's current law at node G, applying KCL at node G. Let us see what we will get. This is the node G. At any node, the sum of currents entering is equal to the sum of currents leaving. This is called as KCL, Kirchhoff's current law. So the currents entering the node G is I1, which is equal to, no other current is entering the node G. Here II is leaving the node G, IF is also leaving the node G. Here in node G, only one current is entering, that is I1. Entering current I1 is equal to sum of leaving currents. What are the sum of leaving currents? II and IF. Therefore, we can write II plus IF. So applying KCL to the node G, we get I1 is equal to II plus IF. Let us call this as equation 1. Now, we know that, let us assume that operational amplifier is an ideal operational amplifier. We also know that for an ideal op amp, Ri input impedance is equal to infinity. So, when the input impedance or when the input resistance of an operational amplifier is infinity, what is the current entering into the operational amplifier? The current entering into the operational amplifier will be 0 because the resistance is maximum. If we substitute II is equal to 0 in equation 1, the equation 1 reduces to I1 is equal to IF. Let us call this as equation 2. So, after substituting II is equal to 0 in equation 1, we get I1 is equal to IF. Now, let us apply Ohm's law and find out what is I1 and what is IF. So, we know that current is leaving from this ground point to this point. So, we have to assume the voltage here is 0 volts and voltage at node G as Vg. Therefore, what is I1? Applying KV, applying Ohm's law to the circuit, we get I1 is equal to 0 minus Vg by R1, 0 minus Vg divided by R1. So, what is this? This is equal to minus Vg by R1. So, I1 is minus Vg by R1. Let me call this as equation 3. Similarly, what is IF? IF, current is leaving the node G and reaching the output. Therefore, this voltage minus this voltage divided by resistance will give me IF. Therefore, what is IF? IF is equal to Vg minus V naught divided by Rf. Vg minus V naught divided by Rf. Let me call this as equation 4. So, first what we did, we applied KCL at node G. We got I1 is equal to II plus IF, that is equation 1. And for an ideal op amp, Ri is infinity, which we have already discussed, the ideal characteristics. Ri, input resistance is infinity. Therefore, resistance is infinity means current will be 0, II is equal to 0. Substituting II is equal to 0 in equation 1, we get I1 is equal to IF. Therefore, I1 is equal to IF, we call it as equation 2. Now, applying Ohm's law to the circuit, we need to find out what is I1 and what is IF. I1 is given by 0 minus Vg by R1, 0 minus Vg by R1, which is minus Vg by R1, equation 3. And similarly, what is IF? This voltage minus this voltage divided by resistance Rf. Therefore, IF is equal to Vg minus V naught divided by Rf. Let us substitute equations 3 and 4 in equation 2. Substituting equations 3 and 4 in equation 2. Let us rub off all this and let us retain I1 is equal to IF, and let us substitute I1 and IF in equation 2. So, what we will get? Minus Vg by R1, which is equal to that is I1. I1 is given by minus Vg by R1, which is equal to IF from equation 2. IF is Vg minus V naught by Rf from equation 4. So, IF is Vg minus V naught divided by Rf. So, this I will call it as equation 5. Now, we need to find out what is Vg here and substitute that Vg value in this equation, and let us see whether this circuit gives us non-inverting version, non-inverting amplifier or not, right. So, I will rub off all this is not required. Now, how to find out Vg? We already discussed the virtual ground concept. What is virtual ground concept? Let us do that analysis here. We know that AV, voltage gain, is infinity. This is also one of the ideal characteristics of operational amplifier. AV is equal to infinity. What is voltage gain? It is output voltage divided by the difference between the input voltages, that is difference between the non-inverting input and the inverting input of the op amp. Therefore, V naught by VID is equal to infinity. If we want to get V naught by VID is equal to infinity, what is the denominator? The denominator VID must be 0, then only we get infinity here. So, VID is equal to 0. So, what is VID? It is the input differential voltage, VID, input differential voltage. What is differential voltage? So, VID can be written as V non-inverting voltage, V I will write, minus V inverting voltage, inverting input voltage, which is equal to 0 as per this. So, what is V non-inverting input terminal? So, the voltage at non-inverting input terminal is Vi. So, this is Vi minus what is V inverting? Inverting, we call it as at the inverting input terminal, node G we marked. What is the voltage at node G? Which is Vg. Therefore, so what is inverting input voltage? It is Vg. So, what is this? Vi minus Vg, which is equal to 0. From this, what is Vg? So, Vg, if you send this Vg that side, we will get Vg as Vg is equal to Vi. This I will write here, virtual ground concept. We will recall what is virtual ground concept quickly. Virtual ground concept. In an ideal operational amplifier, let us discuss what is virtual ground concept. In an ideal operational amplifier, if one of the input terminal is held at some potential, then automatically the other input terminal is also pulled to the same potential. This concept is called as virtual ground concept. Now, here we have maintained Vi at positive terminal. Therefore, due to virtual ground concept, Vg will also become Vi. That is what I showed here. Vg is equal to Vi. That is virtual ground concept. On the other hand, if we maintain one of the terminal as ground potential, then automatically the other input terminal is also pulled to the same ground potential. This concept is called as virtual ground concept, and the virtual ground concept exists only for the ideal operational amplifier and not for the practical operational amplifier. Therefore, due to virtual ground concept, due to this analysis, we got Vg is equal to Vi. Let me call this as equation 6. Let me substitute equation 6 in equation 5, where Vg is there, we will substitute Vg as Vi. So, let us see what we will get in equation 5. So, Vg is there, so it is nothing but Vi minus Vi by R1, which is equal to, wherever Vg is there, I will substitute Vi. So, Vi minus V naught by Rf. So, let us do some mathematics on this. So, minus Vi by R1 is equal to Vi by Rf minus V naught by Rf. I am just splitting this Rf to the denominator of Vi and to the denominator of V naught. If we take LCM as Rf, we get back the same thing. Now, what I will do, I will send this Vi by R1 that side and V naught minus V naught by Rf this side. So, what happens? Let us see. So, V naught by Rf is equal to Vi by Rf as it is, I will retain Vi by Rf minus becomes plus that side Vi by R1. So, what is common on right hand side? Vi is common, and let me send this Rf that side. Therefore, V naught becomes Rf by Rf plus Rf by R1. So, the common thing here is Vi, I will write Vi here. So, what happens? Rf and Rf get cancels now. Rf and Rf get cancels. So, when it get cancels, it will be 1. Therefore, I will write, I will rub off this, I will write V naught is equal to, this is 1 plus Rf divided by R1 multiplied by Vi. So, I can write this as V naught is equal to AF into Vi. So, if I consider AF as some proportionality constant, therefore, V naught is proportional to Vi. V naught is proportional to Vi. You can see here Vi is some input signal, weak input signal. To that some multiplication is taking place, some value is multiplied to Vi. Therefore, we get some amplified signal at the output. And this 1 plus Rf by R1, which I substituted as AF, is nothing but the gain with feedback, Therefore, comparing these two, what is AF? AF for non-inverting amplifier is given by 1 plus Rf divided by R1. So, this is the gain of the amplifier, the gain of the non-inverting amplifier. And also we saw that V naught is proportional to Vi. What did I define the non-inverting amplifier as initially? Non-inverting amplifier is an operational amplifier circuit whose output is proportional to the input version, input signal. So, V naught is proportional to the input. So, equation star I will consider. Observing equation star, we can say that the above circuit works as non-inverting amplifier. Non-inverting means positive half gets amplified and it will retain at the positive side, and negative half is got multiplied by 1 plus Rf by R1 and it got amplified at the negative side. Therefore, no inversion. What is the phase shift between the input and the output? Phase shift is 0 and the frequency will also not altered. So, this is non-inverting amplifier. Let us come to the circuit and see. Yeah. So, I have shown here the circuit, which is this circuit, non-inverting amplifier circuit, and RF, R2 we have taken it here as RF, and this is the circuit diagram. Next, circuit details. I told you first we need to define the circuit definition, then circuit details, and then the circuit analysis. The circuit analysis, let us apply KCL at node G. We get I1 is equal to II plus If, which we have done on the board so far. Since the op amp used is ideal op amp, II is 0 as Ri is infinity. Therefore, equation 1 becomes I1 is equal to If, that is equation 2. Now, from the circuit diagram, applying KVL, we get I1 as 0 minus Vg by R1, which we call it as equation 3. Similarly, If is equal to Vg minus V naught by Rf. Substituting 3 and 4 in equation 2, we get 5, that is 0 minus Vg by R1 is equal to Vg minus V naught by Rf, that is equation 5. Now, for an ideal op amp, we need to explain the virtual ground concept here. For an ideal op amp, AV is infinity. So, V out by V in, VID is infinity. What is VID? VID equal to 0. This means that non-inverting input terminal voltage V non-inverting minus V inverting equal to 0. In the above circuit, V non-inverting input voltage is Vi. Therefore, we take V non-inverting as Vi, V inverting as Vg. So, we get Vg equal to here we get Vg equal to Vi. So, this is due to virtual ground concept. And substituting this in equation 5, we get minus Vi by R1 is equal to Vi minus V naught by Rf. After doing some mathematics on this, we get V naught is equal to 1 plus Rf by R1 into Vi. That implies V naught is equal to AF into Vi, where AF is 1 plus Rf by R1. What is AF? It is the voltage gain of the inverting op amp, or voltage gain of the non-inverting amplifier, or the voltage gain of the non-inverting op amp. Now, Observing equation star. What is equation star? Equation star tells that V naught is proportional to Vi. Observing equation star, the output of non-inverting amplifier is proportional to the non-inverted version of the input. Therefore, the above circuit works as non-inverting amplifier. Now, so we discussed inverting amplifier, we discussed non-inverting amplifier. These are all the applications of operational amplifier. Let us see in some more detail what are the applications of operational amplifier or op-amp applications. The op-amps are used for variety of applications nowadays. Some of the important applications are, we have seen non-inverting amplifier just now, and we have already seen inverting amplifier. We need to see what is voltage follower. Voltage follower is also one of the application of operational amplifier. The comparator, adders, subtractors, differentiators, integrators and precision rectifiers, etc. There are plenty of other applications. These are some of the important applications. Now, one of the important application of operational amplifier is a voltage follower. Let us see what is this voltage follower. In most of the applications in communication area and defense area, we use voltage followers as buffers, buffer circuits. What is a buffer? A buffer is an electronic circuit whose input impedance is very large and whose output impedance is very small. In communications, at the output we come across what is called as loading problem. Due to that loading problem, we may not get the output properly. At that time, we will be using voltage follower circuit as a buffer to match the impedance. So, they are called as impedance matching circuits. So, one of the application of operational amplifier is voltage follower. Let us discuss what is voltage follower. The voltage follower is a op-amp circuit, Voltage follower is an op-amp circuit. You can see this sentence, operational amplifier circuit in which the output follows the input. So, what is this circuit? Operational amplifier is an voltage follower is an operational amplifier circuit in which the output follows the input. That means V naught is equal to Vi. V naught is equal to Vi. Now, the voltage follower, how do we get voltage follower? It is a special case of non-inverting amplifier. So, just now we saw what is non-inverting amplifier. Non-inverting amplifier output is given by V naught is equal to 1 plus Rf by R1 into Vi. If we consider Rf as 0, that means we have to short circuit the feedback path, and if we consider R1 is equal to infinity, then what happens? Then the equation reduces to V naught is equal to 1 into Vi in the non-inverting amplifier. Therefore, V naught becomes Vi. That we will see what is that. The voltage follower is a special case of non-inverting amplifier circuit where all the output voltage is fed back to the inverting input terminal. That means we short circuit the we take out the feedback resistor, we short the output to the inverting input. That is what we can see in the next circuit. So, this is the circuit. So, this is the circuit diagram. So, what we did here, it is nothing but a non-inverting amplifier where we give the input signal to positive terminal or the non-inverting terminal of the op-amp, but what we did here, Rf we made it 0. When we make Rf equal to 0, what happens? It is just a short circuit from the output to the negative input, you can see here. Then R1 we made it infinite. Infinite means it is open circuited. R1 is open circuited. Let us see the board and see what is this. So, this is a non-inverting amplifier circuit. I will say from the non-inverting amplifier circuit, we get the voltage follower circuit. How do we get? V naught is given by 1 plus Rf by R1 into Vi. Just now we saw what is non-inverting amplifier. Now here if I make Rf equal to 0 and R1 is equal to infinity, what happens? The equation reduces to V naught is equal to 1 plus 0 divided by infinity. Anything divided by infinity is 0 itself into Vi. So this becomes 0. Therefore what happens? V naught is equal to 1 times Vi. That is nothing but Vi. So V naught is equal to Vi. That means what? All the output is coming to input Vi. That means we need to make a correction. If Rf is made 0, means it is a short circuit. If Rf is made 0, it is a short circuit in non-inverting amplifier. And R1 is taken as infinity, that means it is open circuited. That means nothing is there here. Now this is the voltage follower circuit. When we make Rf equal to 0 and R1 equal to infinity in a non-inverting amplifier, we get the voltage follower circuit. That's the reason why I told you voltage follower is a special case of non-inverting amplifier circuit, and this is the non-inverting amplifier circuit wherein we apply the input signal to the positive input terminal, that is positive input terminal or the non-inverting input terminal of the operational amplifier. Now let us come to this circuit. So you can see here voltage follower is a special case of non-inverting amplifier in which if Rf equal to 0 and R1 is equal to infinity, and the circuit reduces to this circuit. Now we need to analyze this circuit. Before going to that, what is this circuit? Voltage follower, as output is same as input, hence the gain. What is the gain of the operational amplifier voltage follower circuit? Because gain is given by V naught divided by Vi, and since V naught is equal to Vi in this case, what is the gain? Gain becomes 1. So unity gain circuit. Voltage follower is also called as unity gain circuit. Gain remains 1 here, right? So let us go to circuit analysis. What is the circuit analysis we have to do here? Let us see. So in the circuit analysis, again we need to assume that the operational amplifier is a ideal operational amplifier. For an ideal operational amplifier, AV is equal to infinity. AV is equal to infinity. We know this. And what is this? V naught divided by VID. V naught divided by VID is infinity. This is a virtual ground concept, right? I am keep on repeating this virtual ground concept because this virtual ground concept is very important. That's why for all the applications I am repeating this. This is very important. Please follow this, practice this, and this will be asked as I explain voltage virtual ground concept of operational amplifier in the exam for 6 marks. Definite question. Please go through this. AV is equal to infinity. V naught by VID is equal to infinity. That means that VID equal to 0. VID equal to 0. What is VID? Positive terminal voltage minus the negative terminal voltage is equal to 0. That means here node G is the negative input terminal where the voltage let us call it as Vg. Therefore, Vi minus Vg equal to 0. What is Vg? So Vg is equal to Vi. Now Vg is equal to Vi. This is due to virtual ground concept, and the virtual ground concept exists only for the ideal operational amplifier. I am repeating this point. Be careful, right? So Vg is equal to Vi. Now what is the voltage at G? Vg, which is also Vi. So Vi we applied at positive terminal. Automatically the other input terminal is also pulled to the same Vi. It is virtual ground concept. Since we have shorted this input to the output, what is V naught? What is V naught? V naught is equal to Vi. So V naught is equal to Vi. So what is voltage follower? Voltage follower is an op-amp circuit whose output follows the input voltage. We applied input voltage as Vi and output follows the input voltage Vi through the circuit analysis also. Therefore, this circuit works as voltage follower circuit. That is the analysis. So, in the above circuit, V non-inverting is Vi, the same analysis which I did on the board. So, V inverting is equal to Vg. So, Vi minus Vg equal to 0. So, Vg equal to Vi, therefore, V naught equal to Vi. Hence, the gain, what is the gain of this operational amplifier circuit? The voltage follower circuit gain is given by, this formula. A is equal to V naught divided by Vi. V naught is same as Vi, therefore, we get 1. So, operational amplifier is also called as unity gain op amp circuit, and since it follows the input voltage, it is also called as voltage follower. And since we made R1 is equal to infinity at the inverting input terminal, the input impedance of this voltage follower circuit is very large and output impedance of the voltage follower is very small. So, any circuit which has very high input impedance and very low output impedance is called as a buffer. Therefore, voltage follower circuit is called as a buffer circuit. Buffer circuits are used in many applications in communication area, wherein we make the impedance matching. For impedance matching at the output of any communication circuit, we will be using buffer circuit. One such buffer circuit is a voltage follower. What are the advantages of this voltage follower? As I told you, it provides very large input impedance and it has very low output impedance. These 2 points you can see here. Next, it has low output impedance, so it can be used as a buffer. Buffer is a circuit which has high input impedance and low output impedance. So, such circuits are called as buffers, and buffers are used in impedance matching in most of the electronic applications. And voltage follower also has very large bandwidth. And one of the important application of voltage follower is that whenever we need to check the operational amplifier whether it is working or not, we can just connect a voltage follower circuit, and if we get this, whatever the voltage we apply, 5 volts if we apply at the input, I should get 5 volts at the output. If I apply 20 volts at the input, I should get 20 volts at the output. If that particular op amp gives the V naught is equal to Vi, then we say that operational amplifier is working fine. So, one of the application is voltage follower circuit can be used to check whether the op amp is working or not, working properly or not. So, that is the major application. One of the major application is the voltage follower can be used as a buffer. In most of the electronic circuits, we will be using buffer circuits. And one more application of voltage follower is that it can be used, this circuit can be used to check whether the operational amplifier is working properly or not. So, before using the operational amplifier in certain applications, we need to check whether the operational amplifier is working or not, and that check can be done by using voltage follower circuit. Next, op amp adder circuit. So, what is op amp adder? So far we have seen op amp non-inverting amplifier circuit, op amp non-inverting amplifier circuit, op amp inverting amplifier circuit, op amp voltage follower circuit, and now let us see op amp adder circuit. What is an adder circuit? An op amp adder is a circuit which performs addition of 2 or more input signals, which are applied to the inverting input terminal of the op amp. In fact, we can apply the input signals both either at non-inverting input terminal or at the inverting input terminal. If we apply the 2 or more signals at the inverting input terminal of the operational amplifier, then that particular adder is called as inverting adder circuit. If we apply 2 or more signals which are to be added, is applied at non-inverting input terminal of the operational amplifier and get the output at the output means that circuit is called as non-inverted adder circuit. Our syllabus is restricted to inverting adder circuit. So, let us consider inverting adder circuit. An op amp adder is a circuit which performs the addition of two or more input signals which are applied at the inverting input terminal of the operational amplifier. In other words, an adder is a circuit which is used to perform addition operation on the signals which are applied at the inverting input terminals of the operational amplifier as shown in the circuit. So, this is the circuit diagram. So, here we consider three input signals, one is V1 which is applied to the inverting input terminal, negative terminal which is applied to the negative terminal of the op amp, through the resistor R1. Next, V2 is another signal which is to be added with V1 is applied to the inverting input terminal again through the resistor R2. Similarly, V3 is also one more input signal which is to be added with V1 and V2 which is applied to the inverting input terminal through R3. So, all these signals are coming to inverting terminal. So, two or more signals which are to be added are applied to the inverting input terminal of the operational amplifier like this, and there will be a feedback resistor RF and we take the output at V0, and non-inverting input terminal, that is positive terminal of the op amp, is grounded. So, this is the op amp adder circuit. So, now let us consider this circuit on the board and analyze whether this circuit works as the non-inverting adder circuit or not. Let us consider that here. So, let me consider the same circuit here and let us analyze whether this works as adder circuit or not. So, non-inverting input terminal is grounded, and to the inverting input terminal we apply the signals V1 through R1, V2 through R2 and V3 through R3. So, this is R1, R2 and R3, this is V1, V2, V3, and there is a feedback, negative feedback we can take from here also. There is a negative feedback, this is RF, and now we need to analyze this circuit. To analyze this circuit, we need to consider this as node G, and the current entering into the operational amplifier, as we have considered in all other applications, here also we need to consider II, and we need to consider I1 which is flowing through R1, I2 which is flowing through R2, I3 which is flowing through R3, even you can write here also I3, and the current is flowing in the RF as IF, and this is V0. So, we need to prove that V0 is proportional to minus, because it is inverting. So, inverting adder circuit, minus of V1 plus V2 plus V3. So, we need to prove that this is the this circuit should give this, then we say that this circuit works as inverting adder circuit, or simply it is a adder circuit. Now, let us follow the analysis in the same way which we considered in the last applications, previous applications. Now, applying KCL at node G, applying KCL same analysis. Let us apply KCL. The sum of currents entering the node G is equal to sum of currents leaving the node G. Sum of currents entering are I1, I2, I3 entering the node. So, I1 plus I2 plus I3, which is equal to currents leaving are II and IF. So, II plus IF. Now, II is 0 because the operational amplifier is a ideal operational amplifier. As for an ideal op amp, Ri is infinity which is one of the characteristic, therefore, which implies Ia is equal to 0. So, when we substitute Ia is equal to 0 in this equation, we get I1 is equal I1 plus I2 plus I3, which is equal to If. Now, let me call this equation as 1. Equation as 1. So, I1 plus I2 plus I3 is equal to If, which is equation 1. Now, what are these I1, I2, I3 and If individually we need to find out from the circuit by applying the Ohm's law. So, applying Ohm's law to the circuit, applying Ohm's law to the circuit, we get I1 is equal to, you can see here, I1 is the current through R1, the current is moving from this end to this end, so that is meeting at G, node G. Therefore, V1 minus Vg by R1 is I1. So, V1 minus Vg divided by R1. I1 is equal to V1 minus Vg by R1. Similarly, what is I2? I2 is V2 minus Vg by R2. V2 minus Vg by R2. Similarly, what is I3? I will write here. I3 is given by I3. It is V3 minus Vg by R3. V3 minus Vg by R3. So, what is If? We need to find out If also. So, If is given by, it is Vg minus V0 divided by Rf. So, Vg minus V0 divided by Rf. Let us substitute all these values in equation 1, right. So, I1 is V1 minus Vg by R1 plus I2 is V2 minus Vg by R2 plus, what is I3? It is V3 minus Vg by R3, V3 minus Vg by R3, which is equal to, I am substituting all these values in what? In equation 1. I1 I substituted, I2 I substituted, I3 I substituted, and right hand side If is there. If is given by Vg minus V0 by Rf. So, this is the equation. Here we know V1, which is the applied signal, V2 we know, V3 we know, and V0 we need to find out. R1 we know, R2 we know, R3 we know, Rf we know. Only unknown parameter here is Vg. What is the voltage at node G? We need to find out. So, since one of the input terminal of the operational amplifier is held at ground, automatically Vg is 0. How? We have seen the virtual ground concept. So, for ideal op amp, we know that AV is infinity, which we have seen already. So, V0 divided by VID is infinity, which implies VID is 0. VID means positive terminal voltage minus the negative terminal voltage. Negative terminal voltage is Vg, positive terminal voltage is 0. So, therefore, 0 minus Vg equal to 0. Therefore, what is Vg? Therefore, Vg equal to 0. So, we got Vg equal to 0. Why we got Vg equal to 0? Because non-inverting terminal is held at 0 potential. Therefore, Vg equal to 0. This is due to what? This is due to virtual ground concept. This is very important concept. Every application we come across virtual ground concept. If we consider ideal op amp. So, for an ideal op amp, virtual ground exists. Therefore, here Vg equal to 0. Let us substitute Vg equal to 0 in this equation. So, substituting Vg equal to 0 in that equation, what we will get? Let us see. So, I will rub off all these things. So, therefore, V1 divided by R1 plus Vg is 0. In all these cases, Vg is 0. So, here also Vg is 0. Therefore, V1 by R1 plus V2 by R2 plus V3 by R3 is equal to what on the right hand side, minus V0 by Rf, minus V0 by Rf. So, minus V0 by Rf. So, what is here we need to consider R1 equal to R2 equal to R3 equal to R, F equal to R. If we consider equal resistances in this, what happens? This resistance, this resistance, this resistance and this resistance all gets cancelled. Therefore, minus V0 is equal to V1 plus V2 plus V3. Therefore, V0 is equal to minus of V1 plus V2 plus V3 we get. So, this shows that V0 is proportional to minus of V1 plus V2 plus V3, V1 plus V2 plus V3. So, therefore, this let us call this as equation star. Observing equation star, the above circuit works as inverting adder. This is the conclusion out of the circuit. So, let us recall in 1 minute what we discussed today. Today we discussed non-inverting amplifier, we discussed non-inverting amplifier, then voltage op amp applications, non-inverting amplifier or non-inverting op amp, voltage op amp applications, op amp voltage follower and op amp adder. These are all the applications, op amp applications. These are all the applications of operational amplifier. In the next class, we will see some more applications of operational amplifiers, and thank you for listening to this class. Thank you very much.